Hello, welcome to video 2 on the TTB course. This video is from part 1 of the TTB course. In part 1, video 1 to video 2, we provide an introduction to the material that will be discussed in detail during the remainder of the course. In this video, we provide an introduction to TT systems. If you haven't already noticed this when reading the relevant book chapters, you'll find that the phrases and terms used in the book and in this course that are in small caps, such as TT systems, on this slide, they have definitions that may be useful. These definitions are in Appendix 1 of the ERES2 book. If you have a look at Appendix 1, you'll find the definition for TT systems, for example. The material in this video, the majority of the material in this video is based on the ERES2 book, Chapter 1 and Chapter 2. If you haven't already read these chapters, along with the preface to the book, I suggest you stop the video now, go back and read these chapters before you continue watching this video. So what I'm going to start by doing in this video is providing an overview of what a TT architecture is and what we can achieve when using a TT architecture. I must emphasize this will be simply a quick overview to give you an understanding of what the capabilities of a TT system are. Once we get on to the remaining videos in this course, we will fill in all the details about the techniques that I'm simply going to summarize in the next few slides. So let's start at the beginning. When we say that an embedded system has a time-triggered architecture, we mean that it executes at least one set of tasks according to a predetermined schedule. The schedule determines the order of the task releases, the time at which each task is released, and whether one task can interrupt, that is, preempt, another task. So this simple tick list here, this is a representation of a very simple set of tasks. So this task set is being released according to a predetermined schedule. So we've determined that to meet the requirements of our application, we need to run task A first, then task C, then task B, then task D. The sequence then repeats. Task A, task C, task B, task D. And it will keep on repeating in this way until we shut down the system or we change the system mode. We'll say a little bit more about system modes in a moment. But this is the core of a TT system. Fundamentally, what matters is that the tasks are released in this predetermined sequence. In practice, the usual way in which we achieve this goal of creating a set of tasks that run according to a sequence that's determined and analysed in advance is that we do this using what's usually called a bare metal software platform. So there's no RTOS, no Linux, no Windows. We have one active interrupt per CPU linked to what's usually a periodic timer tick, and we poll our peripherals. I'll make it clear what polling means, if that's a term that's unfamiliar to you. We'll make it clear what that means later on in this video. I should make it clear at this point that you don't need to use a bare metal software platform. Some TT systems are implemented in designs that use an RTOS. You can do that. So that you're not constrained to using a bare metal platform, but wherever possible, this is the preferred platform and the one that we're going to discuss in this video. A key point here is minimal use of interrupts. For some people, that's a pretty challenging idea. People are brought up being used to the fact that an embedded system uses multiple interrupts. For very small systems, use of interrupts isn't a problem. It's easy to understand how the system works. By the time you get beyond system of limited scale, if you have multiple interrupts, it's very difficult to be sure exactly how the system will respond in any particular set of circumstances, because the system has a very large number of potential states reflected by the software and hardware situation on the design. So if we have a particular set of software running, we have several interrupts triggered, exactly how will your system behave? It's very difficult to predict. In a TT design, we don't suffer from those problems. We produce our system, our overall goal is to produce our system in such a way that we can predict exactly how it will respond at all times during the system operation. And this is how we're trying to achieve that. So let's look at a very simple TTC scheduler. So here I have a sequence of periodic timer ticks. So these are coming from a 1 millisecond timer, we're assuming. And we're going to configure this timer so it generates an interrupt every millisecond. Every millisecond we call the timer ISR, the timer interrupt service routine. In this case, I've assumed that that interrupt service routine is called update. So every millisecond this runs. I'm also assuming here that the worst case execution time, that is the maximum execution time for the update function, is less than 1 millisecond. So we're assuming that this task will run, and then this task or function will run and will complete before the next tick happens. If that doesn't happen, if the update function has a worst case execution time that's longer than the tick, it's more difficult to work out what our system will do. So we would expect in this kind of TT design that we would monitor the execution time of the update function at runtime and make sure we could determine if it had ever exceeded that limit. We'll say a little bit more about some simple monitoring approaches a little later in this video. Key thing to note as well is that when the system is not running the update function, we will usually put it into an idle mode. We'll put the processor to sleep. So we assume that in these gaps between ticks, the processor's in sleep mode, in an idle mode. Usually, going into idle mode will save power, but that's not our interest in most TT designs. We put it into idle mode to give us very precise control of the jitter, the variation in the execution time of these timer ticks. Again, I'll say a little bit more about that later in this video. So we would have now, every millisecond we have a timer tick generated, a timer interrupt generated, the update function is called. We might call additional tasks or functions from here, from this update function. We might, for example, have a long switch statement in the code. So this is a simple example of a time-triggered system with what are known as cooperative tasks. You might be more familiar with the phrase non-preemptive tasks. So these tasks, once released, are not interrupted by other tasks in the system. These tasks run until they complete, unless we incorporate some mechanisms that deal with a situation known as a task overrun. Again, we'll say more about all of these topics later in the course. This is a simple example of a TT framework, a bare metal TT framework that can implement a very simple TTC scheduler. If you want to learn more about this kind of framework is discussed in the Embedded C book that I referred to in video 1. However, I don't recommend that you use a framework that's quite this simple in any practical systems. We use this kind of framework simply as an introductory training framework to illustrate to people one of the simplest ways of building a TT system. For more complete TT designs, I recommend that you use a TT scheduler that includes a dispatcher function. I'll say what that means over the course of the next few slides. You'll find lots of examples of this kind of scheduler in the PTTS book that I mentioned also in video 1. And you can download the PTTS book from my company website here. So there are about 1,000 pages in the PTTS book, lots of code examples for a very simple processor. The code can be ported very easily. Systems based on this code are in use across the world in a wide variety of different systems. For a moment. Here, this sounds terribly static. All my system does is it releases task A, then task C, then task B, then task D, then task A, then task C, then task B, then task D. It sounds pretty boring. It sounds pretty inflexible. But the key thing that we need to remember when looking at these systems is most designs will execute multiple tick lists. So this is one simple example. We have one set of tasks, one tick list here, another tick list here, another tick list here. And when we change mode, we change the set of tasks that we're running. So the majority of systems have multiple operating modes. And the key thing, as in this example, is we might have a set of tasks that we use when the plane is climbing, a set of tasks that we use when the plane is at cruising height, a set of tasks that we use when the plane is landing. For example, we may have other sets of tasks, for example, when taxiing, etc. But these three will be enough for us to use in this simple example. The key point is that each of these stages may represent a change in task mode. So we may change mode between this task set and this task set, let's say. Though that change in mode can be event triggered. That is, the change in mode can happen at any point in time. We don't need to predetermine the times at which we change from one task set to another task set. This is very flexible. So in effect, in this design, the times at which we change mode would depend on the pilot's input, on the weather conditions, on the other aircraft in the vicinity, etc. So we have flexibility to change between these different task sets at any point in time in most systems. Many applications contain more than one processor. So what I've suggested is that let's just focus on this processor for a minute, on the master processor. Here we have, I'll assume, a timer ISR driving a simple scheduler on the master node, ensuring that we have time-triggered tasks on the master node. What about the other microcontrollers on this network? Suppose we have these multiple microcontrollers connected together on a CAN bus, for example. It could be virtually any communication protocol we could use, but let's assume it's a CAN bus. If I want to synchronize the activity on all of these processors, so this one's time triggered, but this one's also time triggered, this one's also time triggered, this one's also time triggered. So slave 1, slave 2, all of the slaves are also time triggered, and I also want to synchronize all of the slaves to the master node. We can do that in a very simple way. So when we have the tick generated on the master, what we do is we send a message from the master over the bus to the slaves. The arrival of that message at the slaves generates an interrupt on the slaves. On the slave nodes, there is no periodic timer tick. Instead, the periodic interrupts that drive the simple scheduler on those nodes arrives through the receipt of messages on the communication bus. This is very powerful. Using this approach, we can synchronize activity across multiple microcontrollers. The microcontrollers may be on the same PCB. I'll give an example of that later in this video. And the microcontrollers may be at opposite ends of a factory. So it could be a large design where we're using multiple microcontrollers across a vehicle, across a factory, on the same PCB, and to work together in a manner that we'll discuss shortly. So we can synchronize the activity across multiple processors using this kind of architecture. I mentioned earlier that the tasks here are cooperative or non-preemptive. We can also have tasks that interrupt one another. So again, this would be a time trigger process. Here we have A as a low priority task. At a predetermined time, this task is interrupted by task B, which is a medium priority task. At a later point in time, task B is also interrupted, this time by task C, which is a high priority task. So we have the tasks with multiple levels of priority interrupted at predetermined points in time. As we'll see, this is a flexible approach that can be used with TT systems. As we'll also see, this kind of design can be rendered immune to the challenges of priority inversion, unlike designs based on a traditional RTOS. Again, we'll talk more about that in a later video on this course. So, we've looked very briefly at some of the techniques and some of the things we can do with a TT architecture. The main benefit of this approach is that we can model the system at design time and then monitor the system at runtime to make sure it's operating correctly. So we end up with a three-stage process where we model the system, we build the system, and then we monitor the system, and we make sure that at all times the system behaves according to the original model. Let's take a first brief look at what the model of a TT system looks like. It's very straightforward. So we've already looked at this simple task set. The tick list representing that task set might look something like this. So this is tick 0, we'll assume. We start with tick 0. After tick 0, task A runs, then task C runs. After tick 1, task B runs, then task D runs. And then we go back to the beginning, and we keep repeating this sequence forever, unless we change modes, as we've already touched on. So we can have a simple representation. Our model is usually a text file that lists the task sequences. Once we've got such a model, and again we'll look in detail at this in a later video, but once we've got such a model, we can model the system response times. Suppose task A reads a switch and task D activates an emergency stop operation. We can see in the schedule exactly what the interval is between task A and task D. We can work out the system response times. We can work out the level of jitter, the timing variation in these tasks. We touched on jitter in the first video on this course. We'll say more about it in some later sessions. We can also determine the maximum CPU load for this system. Let's just look briefly at the maximum CPU load question for a task set. So as we touched on in video 1, we're often required to maintain the CPU load within a particular limit by a customer for a system. So we may have a requirement that the CPU load must not exceed 50% at any time during normal system operation. Once we've got such information, we can work out whether we can add an existing task to a given task set without having any impact on the existing tasks that are in that set. So CPU load is an important consideration in many designs. We can calculate the maximum CPU load. This is the maximum, remember, not the average CPU load. The maximum CPU load we can calculate by looking at the complete task set over the hyperperiod. The hyperperiod is the interval after which the set of periodic tasks will repeat. In a later video, we'll talk about how you can work out the length of the hyperperiod. It's easy to do. Once we know the length of the hyperperiod, This, for example, might represent our whole hyperperiod for a given task set. After that hyperperiod, the task set would repeat. So we'd run A, B, C, D, E, F, G, H. Then the hyperperiod would repeat. We'd run A, B, C, D, E, F, G, H again forever, unless we shut the system down or change the system mode. So we have, in this case, 4 tick intervals that we need to consider. To work out the maximum CPU load, we need to know the worst case execution time of each of the tasks in the system. Again, we'll say a little more about that in later videos, and we'll look at some code examples that allow you to work out what the worst case execution time is. Once we know what the worst case execution time is, and we know what the tick list looks like, we can check which tick interval has the tasks released in it that have a combined worst case execution time that is at a maximum level. So in this case, if this is tick 0, tick 1, tick 2, in tick interval 2, if this is tick interval 0, tick interval 1, tick interval 2, if we have a total maximum execution time in tick interval 2 that is the largest one in this hyperperiod, and we can work out from this what the maximum CPU load of the system is. So for example, if the tick interval is 10 milliseconds, the worst case execution time combined of task E plus task F is 9 milliseconds, then our maximum CPU load is 90% from the tasks. We may have to take into account some scheduler load, but again, we can do all of that. So through this approach, we can work out what the maximum CPU load of our system is for any task set. We can also work out and model other parts of the system design as well. Suppose we've gone through and we've modeled our system. At runtime, we need to monitor it. So I've touched on, and we'll look in much more detail later in this course, that we can model various parts of our TT design. But necessarily, these models are based on various assumptions. I'm assuming we have an operational CPU in each microcontroller. I'm assuming that we're running the correct program on each microcontroller. I'm assuming that we have an operational scheduler on each microcontroller. I'm assuming that we can transfer data between the tasks on the same microcontroller without corruption. I'm assuming we can transfer data between microcontrollers without corruption. I'm assuming we have operational peripherals on each microcontroller. I'm assuming that we know the worst case execution times and possibly the best case execution times of all tasks on each microcontroller. And I'm assuming that we know the execution sequence of the tasks in each operating mode on each microcontroller. The really powerful thing about TT systems is we can easily test these assumptions at runtime, and we can work out very quickly, usually on a timescale measured in microseconds, that the system is not operating as required, and we can take action to prevent something unsafe from happening. So a TT design allows us to test these assumptions at runtime and to deal very quickly in a deterministic manner with situations that may arise in which these assumptions are not met. Microcontroller design, just to remind you, we have two microcontrollers working together. These two microcontrollers are synchronized. Microcontroller A might be configured to run the tasks in the sequence that we've looked at several times in this video. So this is what microcontroller A is supposed to do. Microcontroller B is configured to check the task sequence from microcontroller A. But it does this before each task is released. So effectively, microcontroller A sends a message to microcontroller B before it releases each task to say, I'm about to release task B. And microcontroller B will check that that is the correct task. So microcontroller B will hold a separate representation a different representation of what the task release sequence should be, and we'll check that task sequence representation at runtime. This is very powerful. We might have a virus, we might have electromagnetic interference, we might have other problems that cause a disruption in the task sequence. By having the two microcontrollers perform cross-checks, microcontroller A checks the task sequence for microcontroller B checks the task sequence for microcontroller A. We do these cross-checks, we can have much greater confidence that the system is actually operating as required. This is just one of the forms of runtime monitoring that we would expect to perform in a safety-related time-triggered system. So, why should we use time-triggered systems in our design? You may be familiar with MISRA-C. Some people view MISRA-C as a safe or a safer subset of a general class of the C programming language. So rather than using the full C programming language in most safety-related systems, we might use MISRA-C and view that as a safe or a safer subset in our system. Similar issue arises with time-triggered and event-triggered architectures. So we have a general class of event-triggered systems with multiple interrupt sources. Time-triggered systems can be viewed as a safe or a safer subset of this type of event-triggered design. So event-triggered systems are a general class of systems. TT systems are a safer subset of event-triggered systems, in my view. There's support for the use of TT systems in various international safety standards. For example, in the generic IEC 61508 standard, which is widely used as the base standard for many more specific standards. IEC 61508 was the base standard, for example, from which ISO 26262 was derived for use in the automotive space. In IEC 61508, TT architectures are highly recommended for systems of safety integrity SIL 2 or above, safety integrity level SIL 2 or above. Static synchronization of access to shared resources, which is a key characteristic of all TT designs, is recommended for SIL 3 designs and highly recommended for SIL 4 designs in IEC 61508. Limited use of interrupts, a defining characteristic of TT designs, is recommended even for the most basic designs in 61508 and highly recommended for SIL 3 and SIL 4 systems in 61508. More generally, I have never met a certifying authority that has not been happy to see a TT design. TT designs are easy to build, easy to model, and easy to monitor. In most cases where you have to have the design certified, this is a popular option with the certifying authority. If we look at ISO 26262 briefly, Annex D in Part 6 provides examples of faults that can cause interference between software elements. For example, software elements in different software partitions. And this annex provides examples of possible mechanisms that can be considered for the prevention, detection and mitigation of the various faults. And with respect to timing constraints, the effects of faults such as blocking of execution, deadlock, live lock, incorrect allocation of execution time, incorrect synchronization between software elements. According to 26262 Part 6, mechanisms such as time-triggered scheduling, monitoring of processor execution time, program sequence monitoring can be considered. We will use all of these processes in the systems we're working on in this course in order to address the problems identified in ISO 26262 Part 6 and a range of other problems. So we're going to use time-triggered scheduling, monitoring the processor execution time, program sequence monitoring. All of these techniques we're going to use in the various designs that we consider during this course. So let's take a closer look at a first TTC scheduler. So there's a simple scheduler described in the PTTS book that we've already mentioned in this video. You might find it helpful to take a look at that scheduler as some background. It's slightly simpler than the scheduler we're going to look at in more detail in the remainder of this video, but the underlying operation is exactly the same, and you may find it useful to take a look at that, at the examples in the PTTS book after watching this video. What we're going to look at in the remainder of this video is a complete scheduler from ERES 2 Chapter 2. And again, if you haven't read that chapter in the book, I suggest you do so before continuing with this video. So, I'm going to look at what's called in the ERES 2 book TTRD2-O2A. So TTRD2 2A. So you'll find information about this scheduler in Chapter 2 of the book, and you can also find the code, the full code for the scheduler I'm going to discuss on our website at the URL shown at the bottom right of this slide. So you can find all of the code for the scheduler. You might find it useful to take a look at that code before you continue with this video. So the scheduler is made up of the following key components: a task array, an initialization function, a start function, an update function, which is the timer ISR. It has a dispatcher, it has an add task function, and it has a shutdown function. I'm going to look at each of these components in the course of the next few slides. Let's start with the array of tasks. So the tasks in this design are stored in a static and not an array, it's not dynamic, an array of tasks. So this is the scheduler tasks array. For each task represents an element in this array, and for each task we store the following information. We store a pointer to the task, as shown at the top here. So each task in this case is represented by a void function. That is a function without a return value and a function without any parameters. We'll look at some alternative task implementations in a later example, but in this example all of the tasks are assumed to be void functions. We store just two pieces of information about each task. We store a value called delay, which is the number of ticks until the function or task will next be run. And we store a period, which is the number of ticks between subsequent runs of the task. So we have 3 bits of information here. We have a delay value that's updated during the run that says, okay, this task is going to run every, let's say, 10 ticks. And the delay value, it stores the number of ticks, the number of scheduler ticks that will elapse before this task is next released. We'll look at the various details of this example in the course of the next few slides. So to use the scheduler, we're going to do the following things. We're going to run the initialization function for the scheduler. We're going to use the scheduler add task function to add tasks to the scheduler. We're going to start the scheduler using the scheduler start function. In normal operation, the dispatcher, scheduler dispatch tasks, is going to be called. After running all tasks scheduled to run in the tick, we're going to put the scheduler to sleep. The next tick will wake the processor, call the scheduler ISR, and call scheduler dispatch tasks. So it's a sequence of operations that's well defined as the scheduler operates. Let's look at some of those components. First question we need to ask here is, what happens if something goes wrong? What happens if during the operation of the system we detect that there's a problem? So this might be in a washing machine, significant because, as we've touched on, it may be possible to open the door while the machine is spinning, which could cause damage. If our satellite system goes wrong, we may lose contact with it. We may lose a very expensive satellite. If our auto teller machine goes wrong, we may start giving away cash. If our automotive system goes wrong, the passengers or other road users may be injured or killed. So we need to work out, first of all, what we're going to do in the system if we detect a problem. What we're assuming here in this first example is that we can perform a very simple safe shutdown. In other words, we're assuming that we simply fail silently, fail safely, if we detect a problem with the system. So this is the function that we're going to call if the scheduler detects a problem in the system, or if a problem is detected by a task in the system. In this case, all we're going to do is we're going to set up a flashing heartbeat LED. We'll look in detail at this shortly. And all we're going to do is we're going to flicker that heartbeat LED to indicate a fault. That's all that this simple design does if a problem is detected. In a larger design, we'd obviously need to take more action. We need to ensure that the system is in a safe state before we shut it down. We need to do our best to try and disable any dangerous outputs, for example, or bring our vehicle safely to a halt in an automotive example. So the first thing we have to think about is what we're going to do if we detect a problem. Next thing we're going to look at here is how we initialize the scheduler, how we set up the scheduler ticks in the system. And all this code does is it checks to see whether the code for configuring the system tick is configured correctly. This is standard code in an ARM architecture, checking that the system core clock is configured correctly. We then set up our SafeTTy timer. Again, this is standard code for an ARM architecture. We set up our SafeTTy timer, in this case to give us ticks at this number of tick millisecond ticks interval. So typically that might be a 1 millisecond tick, in which case tick millisecond would be 1. We're configuring the SafeTTy timer to give us 1 millisecond ticks in that case. Because the SafeTTy configuration process starts the timer, we need to manually disable the timer and manually disable the SafeTTy interrupt, because we don't yet want to start the timer ticks, not until we've added all of the tasks to the schedule. So that's all we're doing here. We're checking that the system core clock is configured correctly on our device. That should have been done by the manufacturer of our microcontroller or the people that created the code libraries that we're using here. We're then setting up the timer ISR for ticks at an appropriate tick interval, typically 1 millisecond, and then we're disabling the timer ticks and the SafeTTy timer temporarily until we've completed the other parts of the initialization process on our system. So by this point we've got the beginnings of an empty schedule. So we've got the beginnings of a system that would allow us to have our periodic timer ticks, but we've not yet done anything useful with the schedule. What we want to do is add our tasks to this schedule to give us the operation that will by now be familiar to you. To do that, we use the scheduler add task function. So again, you'll find this in the TTRD2A code. What we do in this example is we are adding tasks to our task array. We're doing that by first of all checking to see that there's space in the task array for the task. So we have a scheduler max tasks constant in this example, which is the maximum number of tasks that we can schedule in a particular mode in our system. And we're checking that we haven't exceeded that limit. If we reach the end of the task array, if we can't add any tasks, we treat this as a fatal error in this design, and we shut the system down. We then check, so if we don't have space in the task array, we simply shut the system down. We're then checking for tasks where the user is trying to add a task with a period of 0. We're only allowing periodic tasks. The number of the task period must be at least 1. If the task period is not at least 1, we perform a shutdown of the system. If we've got this far, if we've passed these precondition checks, there's space in the task array, and we add our task to the task array. Once we've added all of the tasks to the task array, we're ready to start the system. So this means that we then enable the SysTick timer and enable the SysTick interrupt in our design. So let's consider what happens during normal scheduler operation. A timer tick wakes the microcontroller and triggers the scheduler ISR, which is called SysTick handler in TTRD2O2A. The function scheduler dispatch tasks is called. After we've run all the tasks that are scheduled to run in a tick, the scheduler puts the system to sleep, and the next tick wakes the microcontroller again. So the process, slightly simplified for this first version, looks a little bit like this. We have the timer ISR. Triggered. This wakes up the CPU. This results in the calling of the dispatcher. Once we've dispatched all of the tasks, we put the CPU back into idle mode, and the process repeats like this. So again, in this simplified model, all the SysTick handler needs to do is to wake up the microcontroller. That's all we would require in this simplified first version of our scheduler. And in this simplified dispatcher, what we would then do when the dispatcher was called is we would work our way through the task array, checking for each task in the array whether there was a task at that location, which means that we don't have a null pointer, which basically usually means that the task pointer is not equal to 0. For each task that has a non-zero task pointer, function pointer, we decrement the delay value. That is, we reduce by 1 the delay value. Once the delay value gets to 0, that means it's time to run the task. So we run the task by means of the function pointer. That's the only bit here that's probably not necessarily familiar to you. You may not have used function pointers before. Take a look at a C textbook to see how this works, but this is standard C code for executing a function by means of a function pointer. Once we've run the task, because all the tasks are periodic, we then set the delay value back to match the period for that task, and the process will gradually repeat. So each task, we decrement the delay value after each tick. Once the delay value gets to 0, we run the task. Having run the task, we reset the task's delay value back to the period for that task. We do this for all the tasks in the array, and then we put the processor into idle mode. So that looks pretty straightforward. And as long as our tasks look like this, as long as all the tasks complete within the tick interval, then everything should be okay. However, there's a risk here. If we don't enter idle mode, then what's going to happen is that we will keep calling. So if you remember, this is what our main function looks like. So if we don't enter idle mode, what's going to happen is we're going to keep going around this loop and repeatedly calling scheduler dispatch tasks. That's not going to give us the behavior that we want. So we'll run the tasks more frequently than we intended. So what usually happens is we use some kind of tick counter variable called tick count G in this example. And what this does is in the timer ISR, we're going to increment the tick count variable. So the timer ISR will do two things now. It will increment the tick count variable, and as a side effect, it'll wake up the CPU. Then we're going to go into the dispatcher, and in the dispatcher, we're going to decrement the tick count variable. So these two will match up. And control of the tick count. So the tick count variable will be incremented in the tick count in the timer ISR, decremented in the dispatcher. At the end of the dispatcher, again, we're going to put the CPU into idle mode. So in this case, if we don't enter idle mode, the scheduler will still operate correctly, because we will still only increment the tick count in the timer ISR. The dispatcher will decrement the tick count. If the tick count is not greater than 0, the dispatcher won't release any tasks. So now we'll get the correct behavior here, whether or not the processor enters idle mode. So this is one way. It's still a bit simplified, but this is one way we can achieve that. So now our sysTick handler includes an increment of our tick count variable in this example. And our dispatcher needs to be modified a little bit too. So now we're checking to see whether the tick count is greater than 0. If that tick count variable is greater than 0, then we set a flag that says there's an update required. And we keep going around this loop, releasing the tasks in the same manner that we talked about a few moments ago. We keep going around this loop, releasing the tasks, and then when we get to the end of the task array, having checked whether any tasks are due to run, we then, only at this point, do we decrement the tick count, but we check it again here. We check again to see whether the tick count is still greater than 0. That could occur, for example, if what our tasks ran, the sum of the execution time of the tasks that we release in a particular tick interval, if the sum of the worst case execution times is greater than the tick interval, then we could have another tick while we're releasing tasks. And this allows us to check for this and to make sure that we catch up and release any tasks that are still due to be released. So the end result is we can run task sets that look like this quite happily using this kind of scheduler. So if this task B in this case, is released in this tick and is still running in this tick, that's fine as far as this scheduler is concerned, and we could run additional tasks and tasks that were much longer than the tick interval quite successfully in this design. So in practice, what we're more likely to do is add an additional checked mechanism. So we've still got now our incremented tick count, but now we check it. We check this tick count against a limit. And if the limit is exceeded, then we're going to shut the system down. So if this is acceptable behavior, where all of the tasks released in a tick interval are designed to complete within that tick interval, then we would set scheduler tick count here to 1, and that would be fine. If we want this behavior to operate, we want the behavior shown in this slide to be acceptable, we could set scheduler tick count limit to 2, and again that would be fine. But if we consider this example again, with scheduler tick count limit set to 2, if this task overruns a bit further, so now task B tries to keep running over the next tick interval, then we're going to exceed the tick count limit, and probably what we will do is enter a fail-safe state. Still one other thing that we need to think about with the idle mode. If you have a look at Appendix 7 in the ERES2 book, you'll see how we can measure the jitter in the tick in our system. In this case, what this example summarizes is that if we put our scheduler into idle mode between ticks, the level of jitter that we see in the tick is too low to measure during the techniques that are described in Appendix 7 of the ERES2 book. If we don't put the scheduler into idle mode, we get a measurable level of jitter from the system. So an additional advantage we're getting from this TT approach is that we've got very fine control over the task jitter levels in the system. So we can control the level of tick jitter very precisely in this TT design. So let's pull together the techniques we've talked about in the last 45 minutes into our complete system. So the code example that you've got, TTRD202A, is designed to run on a simple low-cost Nucleo board. The precise board is explained in the ERES2 book, Chapter 2. We've got a simple switch interface on this board, and we've got a heartbeat LED. So we've got a flashing periodic task. We've got a flashing LED on this system that flashes on and off periodically to indicate the system is operating correctly. In this design, if we push the button, the LED will stop flashing. If we release the button, the LED will start flashing again. So these are how we add the tasks to our system using the add task function. We have a watchdog task for feeding the watchdog. We'll say more about that in a few minutes. It's added with an initial delay, the B value of 0, and it is set to run. The task period in ticks is set to 1. So every tick the watchdog task runs. We have a task for reading the switch. Again, we'll look at the code for that task in a minute. It runs every 10 ticks. In this case, we have a 1 millisecond tick interval, so the watchdog task is run every millisecond. The switch task is run every 10 milliseconds. Our task for flashing our LED is run every 1,000 milliseconds every second. In all cases, we have an offset value or an initial delay value for these tasks of 0. In this example, we set the watchdog timeout to around 2.5 ticks, and we feed the timer at the start of each tick. This is the typical use of a watchdog timer in a TT design. So in this design, we feed the watchdog, we release the watchdog task. The first thing in each tick is the release of the watchdog task. In most cases, what we're going to do with the watchdog timer in our TT systems is to detect and handle failure of the scheduler. We'll say more about this later in the course. This is our complete watchdog module. as with most tasks, we have an initialization function for the task, and then we have the task itself, the update function. So the initialization function is just set here to allow us to set the watchdog timer on this particular processor to an appropriate timeout value. So as we said, that's going to be set in this example to approximately 2.5 ticks. And then we're going to call the watchdog task itself, the watchdog update function, simply feeds the watchdog in this example. Of course, different watchdog code and will be used depending on the microcontroller that we're working with. That was shown here. We're setting up that switch pin as an input pin using this code. Then we have again the update function, which is the task itself here. What this task does is it reads the state of the switch pin, and it determines whether the switch button pressed module global variable here, whether that's set to button 1 pressed or to button 1 not pressed. One of these two constants is used here. You can look through how this code works. So basically we're calling this function repeatedly, periodically, and the periodic calls allow us to determine whether the switch is pressed and allow us to carry out debounce behavior on that switch. Switch button 1 get state from the switch interface task and checks to see if the switch is not pressed. If the switch is not pressed, then we carry out the heartbeat flashing behavior. So we check if the heartbeat LED was previously on, we switch it off. If it was off, we switch it on. We only do that if the switch is not pressed. If the switch is pressed, we don't do this. We just leave the heartbeat LED on or off as it was previously. And that completes our example. You might like to have a look at the ERES2 book and review how this code. That brings us to the end of this video. Before you read the next video, please read Chapter 3 in the ERES2 book. Thank you for watching this video.